Hello, welcome to the NPTEL online certification course on deep learning. You remember in the previous class, we were discussing about the backpropagation learning with respect to some examples. So, what I wanted to do is, I wanted to explain how the backpropagation learning algorithm works with the help of example to have a clear understanding of the backpropagation learning. And the point till which we completed was this, that when you go for backpropagation of the error at the output layer, that means now I want to update the weight vectors connecting the nodes from the hidden layer to the output layer. The example that we are considering is a two-layer neural network or two-layer feed-forward neural network. So, when you go for updation of the connection weights, as the error can be computed only at the output, I cannot compute an error at the output of any of the hidden layer nodes, because I do not know what are the targets or what are the target vectors at the outputs of the hidden layer nodes. But given the class belongingness of the training vector, I have what is, or I know what should be my target output. So, any deviation of the output that you get from the network from the target output, that is my error. So, the backpropagation learning algorithm tries to adjust the weight vectors so that the error is reduced or the error is minimized, and for that you start from the output layer node. So, in the previous class, what we have discussed is that how do you adjust the weights at the output layer nodes using the error information or by backpropagating the derivative of the error information with respect to the weight vectors or the weight components from the hidden layer node to the output layer node. So, for that we had defined these various terms as is shown in this particular diagram. Now, you also remember that in the forward pass, we have computed the outputs of every node in the hidden layer. We have also computed the outputs of every node in the output layer. In fact, that is from there only I know what is my error. So, the outputs of the nodes in the hidden layer are as given here, that x11 is 0.92. So, this is x11, which is the output of the hidden layer node, and similarly x21, which is output of the second node in the hidden layer, is 0.27. And I said that I cannot compute the error in the hidden layer, because though I know from the forward pass that what are my outputs, but I do not know what are the targets, right. So, I cannot compute error in the hidden layer. And in the same manner, I have computed output of the output layer nodes. So, this is my x12, that is the output of the first node in the output layer, which is 0.44, and 0.95 is x22, which is the output of the second node in the output layer. And we also said that the vector 0.7, 1.2 that we considered, this vector is taken from category 1. So, as a result, my target is nothing but 1, 0. This is my target vector, but this is the actual vector that I got. So, the difference between the target vector and the actual vector, that gives me an error. And by using the backward learning mechanism, we have to reduce or minimize this error. That means, this output should be as close as possible to the target output, and that is what we are doing using the backward learning algorithm. So, now let us see. So, as we have seen before, that how this backward learning algorithms. So, I need to compute these terms del j2, that is for j equal to 1 and 2. So, I have to compute del 1 2 x 1 1. So, for various combinations of j and I have to compute this derivative of E with respect to the connection weights. And for this, I need the values that we have computed in the forward pass. So, let us see how it is done. So, I define del j2 as it is already defined, which is x j2 into 1 minus x j2 into x j2 minus tj. So, you remember x j2 minus tj is the error component, the jth error component of the output error vector. So, for different values of j, I compute delta 1 2. So, delta 1 2 is nothing but x 1 2 into 1 minus x 1 2 into x 1 2 minus t 1. And as we have just seen that what is my x 1 2? X 1 2 is 0.44, as is obvious from here. X 1 2 is 0.44 and x 2 2 is 0.95. So, by using this, I go for this computation. That delta 1 2 is equal to x 1 2 into 1 minus x 1 2 into x 1 2 minus t 1. X 1 2 is 0.44 and t 1 is 1, because the input vector that I am considering that to belong to class 1. So, t 1 equal to 1. So, as a result, when you compute this delta 1 2, it simply becomes minus 1.38. Just this computation will give you. And in the same manner, when I compute delta 2 2, which is x 2 2 into 1 minus x 2 2 into x 2 minus t 2. So, you remember that my x 2 2 was 0.95 and t 2 is equal to 0, because the input vector belongs to class 1. So, my t 1 is 1 in the target vector and t 2 is 0 in the target vector. So, accordingly, as x 2 2 is equal to 0.95, when I compute delta 2 2, delta 2 2 comes out to be 0.045. So, simply by gradient descent algorithm, the updated delta 1 1 2 is nothing but delta 1 1 2 minus the updated W 1 1 2 is nothing but W 1 1 2 minus some eta times del E del W 1 1 2. And as I have computed delta 1 2 as minus 0.138. So, del E del W 1 1 2, it is simply delta 1 2 into x 1 1, that is the output of the first node in the hidden layer, that is x 1 1. So, del E del W 1 1 2, which is delta 1 2 into x 1 1, which is nothing but minus 0.126. So, what is x 1 1? Again, x 1 1 we have computed in the forward pass, as you see from here, that x 1 1 is nothing but this value 0.92 and x 2 1 is 0.27. So, using these values, I am computing these quantities. So, this del E del W 1 1 2 is delta 1 2, delta 1 2 is minus 0.138 multiplied by x 1 1, that gives you minus 0.126. And in the same manner, del E del W 1 2 2, which is delta 2 2 times x 1 1, which becomes 0.04. So, as a result, the updated weights, that is W 1 1 2, which is the connection weight from the first node in the hidden layer to the first node in the output layer, that simply becomes W112 plus eta, which is a hyperparameter indicating the learning rate, eta times 0.126. You find that del E del W112 was negative. My learning algorithm, or updation rule, is actually W112 minus eta times del E del W112. As W112 is negative, so this del E del W112, absolute value of that, is being added to W112. Similarly, W122, which is the connection weight from the first node in the hidden layer to the second node of the output layer, that becomes W122 minus eta times 0.04. Now, you note an interesting point over here. That is, after updation, W11, which is the connection weight from first node in the hidden layer to the first node in the output layer, that is being increased, whereas the connection weight from the first node in the hidden layer to the second node in the output layer is being decreased. And you remember that my target vector was 1, 0, whereas the output that actually I have obtained after this forward pass is 0.44 and 0.95. So, that clearly says that I should update the weights in such a way that the first component of the output vector should increase and the second component of the output vector should reduce. That means the output of the first node in the output layer should increase and the output of the second node in the output layer should reduce. And you see that what is this W11 and W12? W11 is the connection weight from a hidden layer node to the first node in the output layer, and W12 is the connection weight from the same hidden layer node, which is the first node in the hidden layer, to the second node in the output layer. So, if I increase W11, then effectively I am adding more values to the output of W1, to the output of the first node in the output layer. And if I reduce W12, as this is weighting at this, as this is being multiplied with the output of the first node in the hidden layer, so the effective contribution, as the weight is reduced, effective contribution to the output of the second node of the output layer, that is being reduced. So, effectively what we are trying to do is, we are trying to increase, by doing this, we are trying to increase this value, this is we are trying to increase, and this value we are trying to reduce. That means, we are trying to move more towards our target vectors. So, this is how it is done in the output layer. Similarly, in the same manner, I can compute what is W21 or the updation of W21. That means, the connection weight from the second node of the hidden layer to the first node in the output layer. This is what is W212, and also W222, which is the connection weight from the second node in the hidden layer to the second node in the output layer. So, in the same manner, by computing this delta 1 2, I can, and delta 2 2, and making use of the outputs of the previous layer nodes or hidden layer nodes, I can compute what is del E del W212. I can also compute what is del E del W222. And here again you find that del E del W212 comes out to be negative, which is minus 0.037, and also del E del W222, that is the connection weight from the second node in the hidden layer to the second node to the output layer, that is also positive. So, the connection weight to the first node in the output layer is negative, connection weight to the second node of the output layer is positive. That means, when you go for weight updation, W212 will be incremented by a factor, by a value which is eta times 0.037. This is the amount which will be added to W212. And similarly, when you update W222, eta times 0.012 will be subtracted from W222. That means, the value of W222 will be reduced, whereas value of W212 will be increased. So, this is a vector which will be increased, whereas this is a vector which will be reduced. So, again, as we have explained before, that this increment of W21 and reduction of W22 tries to make the output of the first node higher and the output of the second node lower. And that is what we should do to reach our target vector, which is 1, 0. In the same manner, the bias term, bias is nothing but W012, which is the bias of the first node in the second layer or in the output layer, and W022, this is the bias of the second node in the output layer. So, in the same manner, you find that del E del W012, that is also negative, that is minus 1.38, and del E del W022, that is positive, which is 0.045. So, all these values will come based on the computations that we have done in the forward pass. So, this also says the bias term, that is W01, once it is updated, it will be incremented by an amount eta times 1.38, whereas W022 will be decremented by amount eta times 0.45. So, this again tries to increase the output of the first node of the output layer and tries to reduce the output of the second node of the output layer, because W01 is being incremented by eta times 1.38, whereas W02 is reduced by 0.045. Okay. So, this is how the nodes in the or the weights in the output layer will be updated. And while doing so, we have propagated the effect of error computed at the output in the backward direction. Now, this error has to be propagated further inside to update the weights from the input layer to the hidden layer. And when you do that, you find that coming to a particular node, you are propagating the weight from the first node, you are also propagating the weight from the second node. So, these two propagating the error from the first node and propagating error from the second node. So, these two error terms are to be added together to consider what is the total back propagated error term at every node in the hidden layers. So, for that, again we have seen before that how this is done. We had defined an additional term, if you remember that when we discussed about the backpropagation algorithm, that for every kth layer node, we have defined an backpropagated error term, which is given by delta ik, which was OIK, sorry, in this particular case we are considering OI to be xi. So, please read this as OI has to be xi, OIK has to be xik. So, please read this as xik. So, my delta ik will be xik into 1 minus xik into sum of delta jk plus 1 wij plus 1. So, you remember that this wij plus 1 is the connection weight from the ith node in the kth layer to the jth node in the k plus first layer. and this delta jk plus 1 is the error term which is propagated up to the jth node of the k plus first layer. So, this is being weighted by the corresponding weight, and you are adding them together to find out what is the propagated error at the ith node. And for doing this, all the nodes to which the ith node has fed the input, that means all the j's, from all of them, now you are accumulating the error by weighting them by the corresponding connection weight and adding them together, and then multiplying that with a local derivative of the output of the ith node, which is xik into 1 minus xik, right. So, once you have this, you define it with respect to k. Now, this k in our case, because we are considering a 2-layer network, the value of k is equal to 1. So, what we have to find out is what is delta I1, and as per this definition, this delta I1 is nothing but xi1 into 1 minus xi1. So, this xi1 is the output of the ith node in the hidden layer. So, this xi1 into 1 minus xi1 into sum of all the back propagated errors from all the nodes to which the ith node has fed the input. So, that is what gives us delta I1. So, given this and all the pre-computed values, all the computed values that we have computed during the forward pass, I can find out what is delta 1 because I know what is x11 from the forward pass. I know what is delta 112, I know what is delta 122 because that is what we had initialized, or in any intermediate stage, in any step of our iteration, these are the updated weights. Those are also known. I also know what is delta 12, that is the back propagated error from the next node, the nodes in the next layers. Similarly, I also know what is delta 22, that is what is the back propagated error up to again a node in the next layer. So, if you compute this, you will find that delta 111, delta 11, that comes out to be 0.24. And in the same manner, you will find that delta 21, that comes out to be minus 0.02, right. So, these are the back propagated errors to the first node in the hidden layer and to the second node in the hidden layer. So, this is the back propagated error to the first node in the hidden layer, and this is the back propagated error to the second node in the hidden layer. So, using this, now I can go for updation of the weight vectors from the input layer nodes to the hidden layer nodes. So, how do I do it? Again, by using the same expressions, your del E, del W111. What is del W111? It is the connection weight from the first node, the connection weight from the first node in the input layer to the first node in the hidden layer. So, that is W111. So, this is the one. So, I can compute del E del W111 as delta 11 times x10. What is x10? x10 is supposed to be the output of the first node in the 0th layer. And in our case, in this case, the 0th layer is the input layer, and what we said earlier is that every node in the input layer gives you an identity function. That means, whatever is the input, it simply passes that to the output. So, this x10 is nothing but the first component of the input vector, which is x1, because that is the input vector, the first component of the input vector. So, this first component of the input vector, if you remember, we considered that to be 0.7. So, my input vector was 0.7 and 1.2. That was the input vector. So, using this, I can compute what is del E del W111 I can compute what is del E del W211, which comes out to be minus 0.014. I can compute what is del E del W211, which comes out to be 0.288. I can compute del E del W221, which comes out to be minus 0.24. I can compute what is del E del 011. Now, del 011, del E del W011, W011, if you remember, it is representing the bias of the first node in the input layer. So, which comes out to be again 0.24. I can also compute del E del W021. W021 is the bias to the second node. So, I can also compute del E del W021, which comes out to be minus 0.02. And once I compute all these, my updation rule, weight updation rule is as before, del ij1 gets wij1 simply gets wij1 minus eta times del E del wij1. Right. So, you find that by forwarding in the backward direction, by back propagation of the error terms from the output layer, I can update the weight vectors even in between the hidden layers, and this can proceed further. So, instead of 2-layer network, if I take a 3-layer network, again the error will be propagated from the second hidden layer to the first hidden layer, and it can be used in a similar manner for multi-layer networks. So, here you find that what we have done, we have just illustrated with the help of examples that in the network layer, at the network level, how the backpropagation algorithm can be implemented to update the weight vectors. And you find that when you use this backpropagation algorithm, the values that you are using at every layer are actually computed in the forward layer, actually computed in the forward pass. So, it will be wise if you save all the values that you have computed in the forward pass for reducing the computation during the backpropagation learning work. And each of these works that you have done, they are independent, every node is independent of the other nodes, so it is highly parallelizable. So, I will stop here today. We will continue with these discussions even at the node level in our next lectures. Thank you.